Sometimes it's quite amazing that I never get calls, but at the moment of starting a class, that's when
Right.
the phone rings. It's like I never ever get calls. It's ridiculous. Okay. Okay. Okay, let's let them through.
Okay.
I'll start sharing. Okay. Morning, everyone. Okay, let's see here. Ah, all right. Okay, so I hope you all finished your assignment on time. There was something I needed to mention. Oh, right. Um, I noticed that. Okay, first let me just ask for questions. Any questions about what's going on so far as people enter the class? No questions or concerns about the assignment, let's say?
Many concerns.
I didn't get that.
Oh no,
Can you
no.
put your
I'm
hand?
just saying there. Oh no, I'm just saying that there are many concerns. That's all. But like,
Oh,
gotta wait until it's created. So
okay. Um. So okay, since we're pretty much at the midpoint of this class, I just wanted to make a couple of comments. So, I think the class is going pretty well in terms of comparisons with other years. I think it's going surprisingly well in terms of like people participating with actually doing good work on the assignments and things like that. Like every year, there are some kind of annoying aspects. And this year it's a little bit worse than others in that respect. Like there's a small group of people who seem to be hell bent. They're very, very motivated to plagiarize. Okay, so to those people, okay, like I don't like to waste my time or the TA's time chasing you guys, the people who decide to cheat. But I just want to make a comment to these low effort cheaters. Keep in mind, okay, that everything that you are submitting to us, everything that you're submitting to the TAs and to me is digital and saved for all time. We have records of everything that you're writing and sending to us. Okay, so for example, if you go on Chegg, put my questions into Chegg, and then get the answer from Chegg and then copy it down in your assignment, the likelihood is, even if we don't go looking for it, I mean, there's actually someone in the department whose job it is to dredge up all this stuff and send it to us. I mean, maybe we won't find it right away. Maybe it'll take us a couple of weeks or maybe a month, but think about it. Just think about what you're doing. Okay, this is all completely besides the fact that it's completely idiotic to go to university and cheat on your very first class on your very first year. I mean, like in terms of, self-help, I mean, that just doesn't make any sense. But just assuming that you have decided that you want to cheat, I mean, could you not find a better way than to do something that it's so easily discoverable? Honestly. Okay, having said that, I think the class is going very well. Any questions, comments? I almost feel like putting a bounty on the Chegs, like giving people points for turning in your classmates. But I mean, come on, that's a little bit Stalinist. I prefer not even to think about it. Anyway, okay, so let's begin. Okay, so we talked about so we introduced some very heavy machinery. The idea that linear, so we're in the middle of studying linear maps between vector spaces, finite dimensional vector spaces over the same field. Okay, and these linear maps are, because of their linearity, it's possible to record them using finite data. The numerical information contained in the map is given by this matrix, by this k by n matrix. And so when we decide that we're going to represent morphisms or maps as matrices, right, what that means is that the composition of maps automatically has some incarnation in matrix operations. And that's how we, ended up with this matrix multiplication with this formula. And so, once we decide that once we decide on the conventions for how a linear map is to be described in terms of a matrix, we automatically get this consequence of matrix multiplication as a representative of composition of linear maps. Okay, now the thing that I want to discuss for the first part of today is that when you take a linear map and you represent it as a matrix, that depends upon the choice of bases, right? And so what we need to understand is how does the explicit description of the matrix, of the linear map, how does the explicit description of the linear map depend upon that choice? So, so this is the next part of this this whole method of matrices. So, so what is the dependence of the matrix let's say the matrix of T, let's say on the choice of bases, beta and gamma. Okay, so so remember that that if we have a linear map, let's say from V to W, with let's say the basis for V is V1 up to Vn, and the basis for W is gamma, going from W1 up to Wk. Right, then remember that the way that we built the matrix, the easy way to remember this is that the jth column, is really T of Vj. So that's what the entries of that column are. So if you remember that, then you'll remember the convention. So the matrix of T relative to the bases beta and gamma is a matrix that has these coefficients Cij, where the Cij entry, if you wanted to figure it out, you would just apply t to Vj. That would be expressed in terms of the Wi's from 1 to k. And the coefficients would just be all the different elements in the jth column. So we would get Cij. Okay, so now the question is, suppose we change bases, change the choices. Okay, suppose that beta prime is another basis for V. And suppose that gamma prime is another basis for W. And so then, so we want to express the matrix representation of this linear map in the new basis in terms of the old representation. So we'd like to see, what the relationship is between the matrix representing T in one basis compared to the matrix representing T in another basis. Okay, so is this, if anyone is confused about the nature of the question, please raise your hand right away before we go any further. The solution to this is pretty simple, but it's, if you don't understand the basic conundrum, then it's not going to make any sense. So, okay, now to do this, there's a kind of clever way of thinking about it, which makes it a lot easier to figure out. So let's just kind of draw the diagram that we're kind of dealing with. So we have two vector spaces, V and W, and we have basis beta and gamma, and we have T mapping from V to W. Okay, but on the other hand, what we're interested in is understanding a slightly different situation where the bases are changed. Okay, now right. So let me get rid of this. Okay, so because we're changing two things, we're changing the basis on the domain and the basis on the codomain. Okay, let's look at each separately. So if we zoom into W, right, then we are we're dealing with the same vector space, but with two choices of bases. You could think of this as being W1 and W2, and then the other basis is something like this, W prime, W2 prime. Okay, and suppose that we want to understand this basis, the relationship between these two bases. There's a kind of clever way of doing it, which is to consider a map, a natural map that we have from W to W. And that natural map is the identity map. It's the identity. Okay, so why is it important to consider this? So think about it like this. So the map is not very interesting. It's the identity map. It takes X to X. However, we have the intent to relate these two bases. So what does the identity map do in the presence of these bases? Well, you could think of it like the following. Like suppose that I wanted to write the matrix of the identity map. Okay, but instead of using, yeah, so okay, I'm having difficulty whenever something is really tautological or kind of like simple, it becomes more difficult to explain. So let's first do an even simpler case. Suppose that we have the identity map from a vector space to itself, and suppose we have a single basis chosen for W. Okay, what would be the matrix of the identity map in this basis? Okay, so I'm using the same basis at the beginning and at the end. So, okay, so this matrix is going to have columns which are given by the identity map applied to, let's say gamma is, W1 up to WK. So WJ, what will happen with the identity map applied to WJ? No surprise, it gets sent to WJ. Okay, the identity map applied to WJ is always just WJ. That's how the identity map is. So what that means is that this matrix is just one down the diagonal. And zeros elsewhere. Because each basis element is just sent to itself. Okay. Now, on the other hand, so let me highlight that. Okay, and the identity map, so the identity matrix, this is called the identity matrix. Okay, and no surprise, it follows directly from what we talked about with composition, that, no surprise that when I take the identity matrix, let me just do the 2x2 case, and I matrix multiply against any other matrix, right? Then what I'm going to get is an unchanged matrix, right? So if I take this row and multiply against this column, I'm just going to get A. And similarly for the next column, B and C. And then this row multiplied by this column just gives D, and so on, D, E, F. So the identity matrix acts as a multiplicative identity in this matrix multiplication. Okay, so so that's the simple case where the choice of basis on the domain and on the codomain are the same. Okay, but what I'm suggesting is that we should investigate the matrix of the identity matrix, the matrix of the identity linear map with respect to two different bases. Okay, because in that case, what will the matrix be? Well, I'm going to have to, so the jth column of this matrix, gamma, gamma prime, is, consists of the coefficients of the identity applied to, let's say, WJ, okay, when we expand it in terms of the new basis. Oops. Oh, I'm sorry. What am I doing? What am I talking about? Sorry. C. Okay, but what is the identity applied to Wj? This is just, let me move this over here. This is just Wj. So what you see is that when you write the matrix of the identity map, but you use different bases for the domain and the codomain, okay, the columns consist of expressing the domain basis in terms of the codomain basis, or the initial basis and in terms of the final basis. So it relates the two bases. These are the coefficients which express one basis in terms of another. Okay, and so this will have, you know, Cij entries, which are you know, non-trivial information concerning the relationship between the two bases. Okay, so where have we seen this before? Well, before, remember, we were expressing, we were taking vectors and expressing them in terms of a basis and writing down the coefficients, right, as a kind of array of numbers. This is very similar to that. It's just expressing it in a slightly different format. It's the columns of the matrix which express the coefficients of each basis element in terms of the primed basis. Okay, so the information is kind of going down the columns, but it's a similar idea to what we were doing with row reduction. Okay, so you can see that the way that we transition from one basis to another is by just considering the trivial map from W to W and writing its matrix. So so this is the idea. If we have a map from V to W and we want to express it in terms of a new matrix, then what we should do is just sandwich it in between identity map for W and identity map for V. Okay, so when we sandwich this map from V to W in the middle of two identity maps, what are we doing to the map? Well, we're not doing anything to the map. The map, if I compose T with the identity, I just get T again. Similarly, with this identity, I just get T again. So the composite of these three maps is just T. Okay, but the basis for the domain and the basis for the codomain of that composition are now changed. Okay, so this is the trick that gives the answer. So to find the matrix of T in the new basis, beta prime, gamma prime, this is what we're looking for. Okay, but this is the same thing as, remember, T goes from V to W. So what I'll do is I'll post-compose T by the identity of W, and I'll pre-compose T by the identity on V. And then I'll write this. I'm not changing, I'm not doing anything. I'm just kind of writing T again, but as a composition of maps, two of which are kind of trivial. They're kind of the identity maps. Okay, but then I can use the fact that that matrix multiplication corresponds exactly to composition. That's what we proved last time. So so then I can write this in the following way: gamma prime T IV beta prime. Okay, but here I need to put what basis for V am I using here? That's what I need to put down here. I need to decide in the composition, right, which bases I'm going to use. So I look up here and I see that the composition that I'm computing is ITI, going from V to V to W, and the bases are as listed here. Okay, so that means that when I express this identity map as a matrix, I'm using beta for the codomain and beta prime for the domain. So that's what tells me that I'm going to put beta. Oops, sorry, that was IV. You always have to be careful about the switching of the order, the way that we write. So this is in beta, beta, gamma, gamma. Okay, and so so this expresses, this expresses the matrix representation with respect to the new bases in terms of the the matrix representation of the original basis. Okay, so I almost didn't do anything. I'm just making use of the technology that we developed last time, but you get something which is very important. So I just want to pause here for questions about this formula. So let me just annotate this. So let's say that the dimension of V, what was it? It was N. So dimension V is N and dimension W is K. So if I wrote this out, just so this is an N by K. And this is equal to another N by K. Okay, and this one here, this is the identity map on V. V has dimension N. So this is an N by N matrix. It's a square matrix. And this one is a K by K, which is another square matrix. Okay, but the dimensions are potentially different. And so one of them would be a, so this one is square, and this one is square. Okay, so the answer to the question of how to express the linear map in terms of the new basis is that we need to take the original representation, this matrix here, and we need to pre-multiply it by a square and post-multiply it by a square. Okay, questions?
So Robert has a good question in the chat.
Yeah, go ahead.
He wants to ask.
I was just wondering if there is, I noticed that the formula for change of basis is awfully similar to the formula we derived weeks ago, where we composed a function with a relabeling on the domain and the range. It's the exact same, it seems so.
Yeah, exactly. So, you know, the very first part of this class where I was talking about finite sets and maps between finite sets and so on, right? And remember, I even gave a description of these maps as a kind of matrix, but in the matrix, we only had ones and zeros. So I intentionally developed that in a way that is completely analogous to this situation. So this thing here, you could think of it as a relabeling in a sense, but it's a generalized relabeling because you're not just taking the basis and permuting it. Okay, you're actually expressing the basis elements as linear combinations of those. So, you know, the main difference between the very first module of the class and this part is that we're allowing to use the numbers in the field to take linear combinations of the elements of the basis rather than just permuting the elements of a finite set. So you know, what you should do is go back to all the stuff that we did before and look at it again with this in mind, and then you'll see kind of what the analogy, how the analogy plays out.
All right, makes sense. Thanks.
Yeah, you're welcome.
Okay, so Yuchi has a question.
Hello, Professor. I want to ask, is the beta prime is same as the beta?
No.
So why it is an identity map? because they are different, why
Yeah.
we can call it identity.
Yeah. Okay. I'll address that in a second. So can I just take the last question, Carl?
Yes. Maybe it's obvious, or maybe I missed something, but I'm wondering what the main motivation is for changing the basis of a set when you're using linear maps.
Okay. We'll get to that. We'll get to that. Just wait on that. Let me just answer
Okay.
the other question. So,
Yeah, cool.
Okay. So be careful. You're making a kind of a category error. You're making a kind of so let's take another look at this. Okay. So there's two levels of discussion here. There's the abstract level, and then there's the explicit level. Okay. Explicit means like numerical computations. Okay. That's what matrices are used for. It's for representing these abstract concepts. So the object that we're studying is a linear map, T, from V to W. Okay, think of a linear map which takes inputs in V and outputs in W. V and W are vector spaces. They don't necessarily have bases. Now, there's an identity map here. If I compose T with the identity map, it does nothing to T. Similarly, I can pre-compose T by the identity map on the domain. That also doesn't affect T. Okay, so T composed with I is just T. There's nothing happening. Okay, but there's also no bases in that statement. Okay, so if I want to describe T explicitly, right, so that I can actually compute in a computer. So for example, an example for what T is, it might be a rotation of a three-dimensional body, okay? And if I want to describe that rotation, on a computer, I would have to take a 3x3 matrix and put numbers in here, right, in order to explain how the thing should rotate. Okay, so how do I do that? I have to choose this beta and this gamma. So I make a choice of beta, I make a choice of gamma, and then what I do is I figure out what does T do to the basis elements. Okay, I have like a certain number of basis elements, n of them. I apply T to each of them, and I put the results in a matrix like this. So I get a whole bunch of numerical information which represents T. Now, I hope it's clear that representation of T depends upon the choice of the basis beta and the basis gamma. Yuchi, is that okay so far? That the matrix that I use to represent T depends upon the choice of beta and gamma.
Yes, I understand.
Okay. Now, if I change the basis gamma, right, then the numerical representation of the matrix will be different. Okay, because if T takes, a basis element V1 to a certain combination of the W's, right, then if I then change the W's completely and re-express T of V1 in terms of the new basis, the numerical constants will be different.
Yes.
So I need to figure out how to relate the matrix of T relative to beta gamma to the matrix of T relative to beta prime gamma prime. Okay, and so look at the formula here. So this is the matrix representation of T relative to beta prime and gamma prime. Okay, but now I'm going to write this. Look at this equality. What have I done? I'm not changing the basis, and I'm not changing the linear operator. The linear map is also the same. I have T, and I have T composed with the identities, which do nothing. Okay, and then I use the fact that composition of linear maps corresponds to matrix multiplication. So I decompose each of these three operators into matrices: matrix, matrix, matrix. Okay, and then here comes the trick, which is that when I do that, I need to decide which bases I'm using on the intermediate space, because this is going from V to V to W to W. So I need to choose not just basis beta prime and gamma prime, I also need to choose basis here and here. Now, if I choose beta prime and gamma prime here, if I choose the same basis that I did on the domain V, okay, then the identity map will just have ones. It'll just be the identity matrix. But I'm not using the same basis on the domain here. I'm using a different basis, beta and gamma. Okay, so you have to understand what the meaning of this is. What is this? This is saying the following. What are the columns of this matrix? They are, if you take a basis element in beta, you apply the identity map to it. What happens to it? Nothing. But now I express that in terms of the new basis. So what this matrix is, even though the identity is there, right? You're thinking the identity doesn't do anything, right? That's true. But if I ask the following question, if I say apply the identity to the basis beta or beta prime, right? It's going to do nothing to that basis, but then I write it in terms of the old basis beta. And that's going to be non-trivial information in the columns of this. So the columns of the identity operation might be non-trivial, depending on which basis you choose for the domain and the codomain.
Yes, I think I understand. Thank you.
So what's happening here is that, the columns of this matrix, the columns here, this is expressing T of V prime, T of V prime in terms of W prime. Here it's T of V in terms of W. This is expressing V prime in terms of V, and this is expressing W in terms of W prime. Okay, so that's what these are all. What this idea is saying is that if you are given, let's say, the matrix of T with respect to V and W, beta and gamma, okay, and if you know W, how to express W in terms of W prime, and if you know how to express V prime in terms of V, then by doing a matrix multiplication, you end up figuring out T of V prime in terms of W prime. We're going to do examples of this later.
Okay, thank you.
Okay, Professor,
yeah.
Didn't you mean W prime in terms of W? Or
no? Look at what's happening here, right? This is what's on the domain, and this is what's on the codomain. Okay, so you have to be careful about the order and the direction of kind of the information flow, right? Because this one has to do with V and W. So you need to you could kind of think of it like
I get it. Yeah.
Okay.
Yeah. Thanks.
Okay, so I'm going to continue now. Yeah, this idea is going to make a lot more sense once we do some examples. Okay, wait. Everything is getting. Okay, so let me do an example. Okay, so suppose that we take a two-dimensional rotation. What is this? So this is a map from R2 to R2. It's basically rotating by a certain angle theta. Okay, and the way that we should interpret this is that we have in R2, we have two standard basis elements. We have E1 and we have E2. Okay, and the information contained in here, let me call this R. The information contained in here is that R applied to E1 is cos theta sine theta. And R applied to E2 is minus sine theta cos theta. The two columns. So that's what that's what R is doing. Okay, so so since I'm writing this map in terms of, right, so and I just want to make it clear. So if I take a general, for a general vector x, which is, let's say x, let's call it v, xy in R2, and R applied to v is matrix multiplication by a vector. So that's a 2x2 matrix multiplied by a 2x1 matrix. And this will give me, cosine that will be the first entry, and then sine theta x plus cos theta y as the second entry. And this tells you how to rotate any vector inside R2. Now, okay, because I'm giving this linear operation as a matrix, what that means is that I'm secretly already using bases, right? I'm making use of bases to write my linear map automatically, okay? Now, what bases am I using? I'm using E1 and E2. What this means is that I'm sorry. So what I meant to write is this. So let me write this a little bit more precisely. 1 second. So what this means is that R, if I apply it to the E1 basis element, right, I get this vector, which I can express in terms of E1 and E2. When I do that, I get this expression. Sorry, this is what I meant to write. Or yeah, maybe even better. Oops. You can see that the coefficients of E1, of RE1, in terms of the E1, E2 basis, are exactly the columns of R. RE1 and RE2. Okay. Now, what I want to do is change the basis. I want to change from my standard basis to a different basis. To gamma. Okay, wait, I just want to make sure that I'm doing this in not a confusing way. So So R has been described using basis E1, E2, and I'll give that the name beta. So that is to say, this cosine 2x2 matrix, this is the matrix of R in the beta basis for the domain and the beta basis for the codomain, because the domain and the codomain are the same in this case. It's just R2. Okay. Now we want to change basis. To gamma, and what will be the new basis? Well, I have a preferred basis for this linear transformation. So my new basis will be the following: 1i and 1 minus I. Okay, that might be a little confusing. Where did these i's suddenly come from? So this is not a basis for R2. So what I've written is completely wrong. Okay, so let me put a comment to correct that. Oops. Okay. And let me say that instead, now what we're going to do, let's view R as a linear transformation from C2 to C2. Okay, there's nothing stopping us. The entries of this matrix are real numbers, but real numbers are special cases of complex numbers. So instead of viewing this as a transformation on R2, I'm just going to view it as a transformation on C2. Okay, and after so what would be an appropriate basis for C2? This basis is still an appropriate basis for C2, right? This is a vector in C2, and this is a vector in C2, and they form a basis for C2. So I've just enlarged, the space that I'm considering, but I'm keeping the matrix the same. I'm keeping the linear transformation the same, and I'm keeping the basis the same. But now I want to change the basis to this basis, which is a basis for C2. Okay, so how do I figure out the matrix of R with respect to gamma? Well, this is the trick that I used before. And what I'm going to do is use intermediate bases beta and I get this this relationship. So what I need to do is I need to take my original cos theta, sine theta, minus sine theta, cos theta matrix and multiply it, pre-multiply it, or multiply on the right by this I gamma beta matrix, and on the left by I gamma beta like this. Okay, now, I'm sorry, I'm not being careful about writing the square brackets. Okay, so so that means that what I need are these two matrices. Now, what are these matrices? Well, this one is expressing gamma in terms of beta, and this one is expressing beta in terms of gamma. Okay, so one of them is going to be easy, one of them is going to be a little more difficult. So if I look at gamma, how is gamma presented to you? It's given as 1i and 1 minus I. So that means that in terms of the standard basis, we could say that, So let me give these names. Suppose this is like W1 and W2, right? So W1 is, so if I try to figure this one out, oops, sorry, I'm trying to go too fast. If I want to figure this one out, the columns will be the expression of W1 and W2 in terms of the standard basis. Well, that's easy to figure out because W1 is just given as an ordered pair. So that's going to be 1 times 1, 0. This one is 1 times 1, 0 plus I times 0, 1. Okay, so I put 1 and I there because it's expressing gamma in terms of beta, beta being the standard basis. And this one here is 1 times 1, 0 minus I times 0, 1. And so I'll put 1 and minus I here. Okay, now what about this one? Well, this one is different. I need to do the opposite. I need to express the W, I need to express the standard basis in terms of the W's, right? So I need to write the standard basis 1, 0 is equal to something times 1I plus something times 1 minus I. Okay, so how do I do it? Well, clearly I can just, if I take their sum, the i's will cancel out. And I'll just get 2, 0. So if I multiply them by 1/2, I should be okay. 1/2 plus 1/2. Okay, and then 0, 1. So as a result of that, I should put the 1/2 here and the 1/2 here. Okay, and then 0, 1. How do I express 0, 1 in terms of W? I need to figure out what the coefficients are. Like this. Okay, and so here it will be useful to multiply by I. So if I do minus I over 2 on this one, and if I do plus I over 2 on this one, then that will give me a cancellation in the first component, and the second component will give me 1/2 plus 1/2, which is equal to 1. So then here the coefficients are minus I over 2 and I over 2. Okay, and then I can multiply it all out. So I can, if I multiply this out, okay, then you can, if I do this first, suppose, then I'll get, well, maybe I should let you guys compute them yourself. So this will give me, you have to do this computation on your own. Okay, so it turns out that the resulting matrix after changing the basis in this way is a diagonal matrix, which is everyone's favorite kind of matrix. Diagonal matrix is really the favorite kind of matrix because of the fact that that every basis element is just scaled, right? This is saying that, so this is giving us the information that in the basis 1i and 1 minus I, the rotation, okay, it doesn't rotate. What it does is it actually just scales 1i by the number this number is otherwise known as e to the minus I theta, and this one is known as e to the I theta. So it scales one I by the complex number e to the minus I theta, and it scales one minus I by e to the plus I theta. Okay, so you might say, well, okay, in the complex plane, multiplication by e to the I theta is still a rotation. That's true, but from the point of view of the complex numbers, what we have is a basis, which each element of the basis is just multiplied by a scale multiple in the complex numbers. So from the point of view of complex geometry, we're not rotating, we're rather just rescaling each basis vector by a different constant. Okay, when we have this type of scaling behavior, these are called eigenvectors and eigenvalues, but we're going to get to that later. So this is called, for later, this is called an eigenvalue. And this is called an eigenvector. Okay, so this is a very this is a very kind of common reason why you might change basis. The idea of changing basis is that you want to make a better choice of the basis so that the linear operation looks simpler. Okay, we saw this before in the case of sets. Remember that we did some exercises and I did some examples where we relabel, okay, the labeling of the finite sets in order to make the map look simpler, like maybe looking like a cycle in cycle notation or something like that. So it's a similar idea that the representation depends on the choice of basis, and there might be some preferred ways of representing a certain transformation to make it simpler or easier to understand. Okay, this is an example. This is a good example to think about. So this is let me just give a name to what this example kind of signifies. So this is like so the idea here is that in the standard basis, the rotation is not diagonal, but in the new basis, it is. So the basic behavior can look somewhat different depending on which basis you're using. So any questions about this? Maybe Charlie?
Yeah, so I just had a question about when you're going from, when you're saying the basis, or when you're saying it's scaling one I by e to the negative I theta.
Yeah, that's this.
Yeah, is that
here.
like, I'm not very familiar with complex numbers, so is that just like a property of them? The cos theta minus I sine theta is equal to e to the negative I theta?
Yeah, I mean, if you take the unit circle in the complex plane,
Mm-hmm.
that is where number 1 is. That's where I is.
Yep.
And this is where e to the I theta is.
Oh.
And so the real and imaginary components are cosine and sine.
Oh, that's cool.
It certainly is. Okay,
Thank you.
Omar?
So what exactly would be the identity map?
What? Say again?
What exactly is the identity map for the for the two bases?
Okay, so be careful here. Okay. Okay, so T goes from V to W. Okay, so there's no such thing as an identity map from V to W. That makes no sense at all. But from V to V, there is an identity map, which just takes every vector and sends it to itself. The identity map just sends X to X. That's what the identity map is. Okay.
Yeah, and what? Which is it? Like, what is it here in this case?
I don't understand your question. So there's something going on here, right? Where I need to express the matrix of T in a different way. So what I'm going to do is I'm going to compose T with the identity map. What does that do to T? Nothing. Okay, so I'm just writing T. This is the thing that is confusing, but it's because there's a concept embedded in here which you need to understand. So the operator, the linear map that we're considering is T. And I can write T like this: identity on V, apply T, and then identity on W. Why can I write it this way? Because the identity does nothing. Identity sends X to X, T sends X to TX, and then identity sends TX to TX. So T is equal to ITI. But the point is that the matrix of the identity doesn't need to be trivial. This square matrix. Okay, this. Oh, I'm sorry. Maybe.
Yeah, I was referring to the
maybe in the example, right?
Complex numbers. That's what I mean.
So if we look here, right? Oops. So I had two bases. I have the standard basis. This one here is the basis 1, 0, 0, 1. And this is the basis 1i, 1 minus I. Okay, so when I write the identity matrix, when I write the identity linear operator using this basis for the domain and this basis for the codomain, I get this matrix. So this does not look like the identity matrix. Okay, but the reason that it doesn't look like the identity matrix is because I'm not using the same basis for the domain and the codomain, which is something that you normally wouldn't do. Normally, when you're trying to describe the identity, the right thing to do would be to choose the same basis on the domain and the codomain because they're the same. The domain and the codomain are both V, right? And if you use the same basis, then the identity just takes each basis element to itself. So what we're doing is we're writing a very easy operation in a very non-easy way. Okay, because we want to encode the relationship between these two bases. How do you encode the relationship between these two bases? You just write the identity operation.
Oh, okay. So my main confusion was like, oh, which one is like the identity and yeah.
Which one? What do you mean? Which one?
I meant by like the the identity of the basis B and R like that. So never mind. I got what I needed. Thank you.
Okay. Okay. Diba, last question, and then I'm going to go to break.
Yes. Okay. So in this example, we started with a basis over R2, and then we kind of put it into a bigger space, so to speak. Like we ended with a basis in C2. We couldn't go the other way, could we? Like we couldn't start with a basis in like a larger...
The basis that I started with was a basis for R2, and R2 is inside C2. Mm-hmm. So R2 is a subset of C2. And so those two elements inside R2, they are two elements in C2, and those two elements in C2 are bases. Now, on the other hand, you know, these elements are in C2, but they're not in R2. Mm-hmm. So the process is not symmetrical. Okay. I mean, the original basis was a basis for R2, and it functioned very well as a basis for C2 as well. But this only works, this only functions as a basis for C2, and it doesn't provide anything for R2. Mm-hmm. Okay, so this is kind of, it's a good example to think about because the rotation of R2 is a typical example of a operation of R2 that cannot be diagonalized. You know, because every vector is rotated in R2, that means that no vector is sent to a multiple of itself. So another way of saying it is that there are no eigenvectors for the rotation of R2. But if I think of the rotation of R2 as a rotation of C2 instead, so if I enlarge the space, okay, then it turns out that I have a greater choice of bases that I could use. And I can find a basis, which I didn't explain how I got it, but we're going to do that later, of how to find eigenvectors, that there is a basis of C2 of the enlarged space, which if I use it, the matrix of the operation looks diagonal. And that's something that you can only do once you enlarge the space. And that's what I'm trying to explain here, is that the enlargement of the space is what allows you to find this interesting basis, which involves I. Okay. Okay, let's come back at 12:25. I'll be back. Okay, welcome back. Okay, so not surprisingly, we need to do a quiz. Just try not to get your adrenaline going up, spiking too much. 1 second. Just take a deep breath. Okay, so we're going to go until 12:32. Okay, let's start.
What is question 4 asking?
These are all true or false questions. This is a statement, and you have to decide whether it's true or false.
I think it was just hidden from view for a bit. So I have it now, though.
Could you let us know if there's like a minute left?
Okay. All right, please enter your last answers. I'm closing it in a few seconds. Okay. Let's see. Linear subspaces always have 0, so they can't be they can't have an empty intersection. Pretty much everyone got number 2. Okay, so number 3 for some reason is the only one that people screwed up on. Let's take a look. So if you have a linearly dependent list, then each vector must be a linear combination of the other vectors on the list. Okay, so
sorry, we can't see the results.
oh, sorry.
Thank you.
Yeah. Okay, so the results are pretty good, except for well, they're excellent except for number 3. So for number 3, if we have a linearly independent list, what does that mean? If you have a linearly independent list, that means there must be a non-trivial linear relation, at least one non-trivial linear relation, which means that there must be a selection of vectors, maybe all, maybe only 2, okay, which satisfy some redundancy condition. A linear combination of them is equal to 0. But that does not have to include all of the vectors, right? So if we have if we have 100 vectors on the list, which you could easily have in an application, and if it's true that v1 is equal to v2, but the rest are all linearly independent, so there's only the redundancy only occurs within a subset of the list, right? The whole list is going to be redundant because of that. You're going to have linearly dependence for the entire list just because of 1 or 2 little vectors that are related to each other. It does not mean that that this vector can be expressed in terms of the previous one. It only means that v1 can be expressed in terms of v2 and vice versa, right? So linear dependence is a redundancy somewhere in the company. It doesn't mean that just because you have 2 accountants, one of whom is redundant, it doesn't mean that you should fire the guy who fixes tires. That's not relevant. Okay, now let's continue with, other than that, it's pretty good. Everyone seems to have a good handle. Okay, now there's 25 minutes left, and I need to get, take a screen cap or something of the poll, because I'm going to stop sharing it in about 5 seconds. Okay, so so in the remaining time, I need to teach you a kind of simple technique, which is going to be used a few times in the following, and it has to do with thinking a little bit more deeply about the Gaussian elimination algorithm and elementary row operations. Okay, so it has to do with this idea of bookkeeping. Okay, now so remember that if we had so in the Gaussian elimination algorithm, right, we had we started with a list of vectors. Let's say, for example, v1 and v2. Let's say v1 is e1 plus 3e2 in terms of the basis that we choose at the beginning of Gaussian elimination. And let's say that v2 is 2e1 minus e2. Okay, so then what we do in the usual Gaussian elimination was that we just wrote down the important data. as a matrix. And then we apply row operations in order to produce a new list. So we're going to produce, so let's say what I could do is use the first row to kill the 2. So that will give me 0 and -7. Then I can scale the -7. Sorry. So this is a shear, a scale. So 1, 3, 0, 1. And then I can use another shear to get 1, 1, 0, 0, 1. Okay. And so this means that the final list is V1 final is equal to just E1 plus 1 E1 plus 0 E2, and V2 final is E2. So what does this mean? This means that we started with the initial list. We end up with a final list, and these have the same span. So this is telling us that V1 and V2 have the same span as the basis, and so that means V1 and V2 functions as a basis. It is a basis. Okay. Now, I did this without bookkeeping. This means that you see that there's a whole bunch of intermediate steps. Like, for example, if I look at the second step, right? The next step is the second list is V. Let me call it 2 and V2 2. The second list of vectors. This is going to be that's going to be okay. So sorry, let me explain what I'm trying to get at. So the point is that okay, suppose I ask the following question. That's the better way to say it. So if we ask, sorry, I'm just trying to reformulate this on the fly, but we'll get there. So V final, V2 final, this is the output of the Gaussian elimination algorithm, has the same span as V1, V2. Okay, but suppose we ask the question, if they have the same span, can we express V1 final and V2 final in terms of V1, V2? Of course, it must be possible, right? I started with V1, V2. I did some row operations to them. I replaced that list with a different list, which has the same span. And so therefore, I should be able to write the final list in terms of the first list, right? So, but I didn't keep track of all that information. In particular, for example, from the first step to the second step, right? What did we do? Let me call it V1 prime, V2 prime, after the first step, okay? And the new list, how does it relate to the old list? Well, remember that V1, I didn't change. I left that one alone. And V2, I got it by taking V1 and using it to kill off the 2 here. So V2 is actually the original V2 minus 2 times V1. Okay, and the new V1 is just the old V1. So every step of the Gaussian elimination, I'm doing, I'm modifying V1, V2 to V1 prime, V2 prime. Okay, and so what I'd like to do is to keep track of that, right? So how do I do this? To keep track of the operations used in Gaussian elimination. So the way that we do it is the following. It's called bookkeeping. Okay, and you should think of it like this. So we have, initially we had V1 is equal to E1 plus 3E2. And we had V2 is equal to 0 times E1 minus 7 times E2. Okay, and I put the, whereas if I look at the second step, so initial, and then the first step, okay, is that I'm going to do a row operation, which is the, oh, sorry, this is, I'm sorry, this is wrong. This should be 2E1 minus E2. And in the first step, I use the shear, right? So I know that I should put E1, 3E2 unchanged here, and then I'm going to subtract 2 times the first row from the second row, so I'll get 0 times E1 minus 7E2. Okay, but I should do the same thing, exactly the same thing on the left-hand side. V1 is unchanged, but V2 is going to be sheared by minus 2 V1. Okay, so bookkeeping is very simple. You just keep track of the left-hand side as well as the right-hand side as you do these operations. Okay, and so you can see that, let's see, the next stage would be scaling. Oops. So I would have to divide by minus 7. So V1 is again unchanged, but I'm going to get minus 2 minus 2/7 V1. Oh, sorry, I'm dividing by minus 7. So I'll get 2/7 V1 minus 1/7 V2 is 0 E1 plus 1 times E2. Okay, so you see what I'm doing here. I'm doing the same operations as before. I'm simplifying the matrix on the right. Okay, but I'm keeping track of what's happening to the list, to the original list, right? So here, for example, after the first and second steps, I can see that that after 2 steps, the vectors that I'm getting, the first one is V1, and the second one is this linear combination of V1 and V2. So I can express this in terms of the original given list. You see what I'm saying? So how do we do this in a more efficient way? Well, you just take a look at this, right? The matrix on the right-hand side is 1, 3, 2, minus 1, just like it was before. But on the left-hand side, I have an identity matrix. So I write the identity matrix on the left, and I consider it a bookkeeping matrix. So more efficient, we write an identity matrix, maybe a bar, to separate it, and then we put 1, 3, 2, minus 1. Okay, and so this is called the bookkeeping matrix. It's just an identity matrix. Okay, and so this is going to go to, oops, let me just do it. So this was going to go to 1 minus 2, 1, 0. This is now, I wanted this. Now the next thing is to divide by minus 7. I wanted this 1 here, right? And you could even go one step further. This is already in row echelon form, but I could go one further and kill the 3 upstairs. So I'm going to do a shear. I'm going to subtract 3 times the bottom row from the top row. So this will be 1 minus 6/7. So I'll get 1/7, 0, and leave the second row alone. And this is reduced row echelon form. Oh, I'm sorry. I forgot to subtract the second one. So I had to do, what I did was I subtracted 3 times the bottom row from the top row. So that's going to give me a 3/7 here. Okay, so this is telling me that if I reinterpret this, what do I get? This left-hand matrix represents 1/7 V1 plus 3/7 V2. And the right-hand side represents just the basis that I chose, E1. And then 2/7 V1 minus 1/7 V2 is equal to E2. So you see that not only when I do it this way, so let me interpret this. This is saying V1 is E1 plus 3E2, and V2 is 2E1 minus E2. Okay, so this is the initial data. I'm expressing V in terms of the E basis, and then the final data is doing the reverse. It's expressing the basis E in terms of the V's. Okay, so you can see that that we're getting more information. So the idea is that originally what we did was we said, take V1 and V2, express it as this square matrix, do the process until we get something that has the same span. So from this we conclude that V1 and V2 have the same span as E1, E2. Okay, and therefore they form a basis. But then we might answer that remark by saying, well, okay, if V1 and V2 are really in the span of E1 and E2, then tell me what combination of V1 and V2 can I use to produce E1 or to produce E2? And this is what the bookkeeping matrix tells you. Okay, so it's basically reversible now. Putting the bookkeeping matrix is, makes it a lot more symmetrical. You could kind of take this sheet of paper and rotate it by 180 degrees and it would look kind of similar. Okay, any questions about the process of bookkeeping?
All right, so Omar has, I think, a question from before.
Okay.
Oh no, that was just
Not anymore. Okay.
Okay.
like raised.
Okay,
So-
Dharmik? Dharmik, is there a question? Okay, you're muted.
I'm sorry, I accidentally raised my hand.
Please go ahead.
I don't have a question.
Okay. So, all right. Now this bookkeeping method is very useful. Well, okay. Let me just explain something important about this bookkeeping method. So, row operations and bookkeeping. Okay. So here's an important fact. Like I just want to remark on something really important about row operations and matrix multiplication and bookkeeping. Okay, so if we have, let's say that we have a product of 2 matrices. Okay, then AB is equal to C. Okay, note that the, if we're interested in a certain entry in C, the way that we get it is that we have to take the row of A corresponding to the row of the element and the column of B corresponding to the column of the element. And we need to multiply those together. So we basically multiply this by this, plus this times this, and so on. Okay, so what I'm trying to indicate here is that when you have a product of matrices, the row is correlated to this row of A, and the column is correlated to the column of B. Okay, so if I was interested in looking at, let's say, all of the entries on this row of C, okay, I would not need any information from A except what is in the corresponding row. If this is the first row, then I need the first row of A. And that will give me all the elements on the first row of C by just taking this row and multiplying it by all the different columns here. Okay, so the conclusion of this is that if we do a row operation on A and then multiply, this does the same row operation on C. Okay, so the rows of C, the rows of a product, okay, are correlated to the rows of the initial matrix, and the columns are correlated to the columns of the final, of the second matrix. Okay, so because we're doing row operations in Gaussian elimination, I mean, we could do column operations too, but just I don't want to make things too complicated. So because we're studying row operations, right, that means that if we were interested in the row operations on C, this would be the same as doing the row operations on A and then multiplying. Okay, so there's a kind of cooperation between matrix multiplication and row operations. And that's what this is supposed to indicate. And kind of the important thing about this is the following. So a consequence of this, so a corollary, is the following, that let's say that I want to do, let's say I have a matrix and I want to do a certain row operation to it. Let's say this is a K by N matrix. And I want to take the rows and I want to do some operation on it, like flipping two rows or multiplying a row or shearing rows. Okay. Now, similar trick as before. Suppose that I put now a K by K identity matrix in front. Okay. Then it's definitely true that AB is equal to B. So if you want to do a row operation to B, you can equally well do it to might as well just write this matrix what it is. It's the identity. So a row operation on B is the same thing as a row operation on I times B. Okay, but this means that we can actually do the row operation to the identity matrix and then multiply. So a row operation on B is the same as a row operation on I multiplied by B. Okay, so let me see. So that I don't confuse too much, let's do a kind of example. So suppose that I have a matrix. And suppose that I take this identity matrix. Okay. Suppose that I wanted to switch the first row and the second row of this matrix. Okay. If I want to switch row 1 and row 2, well, what I'm claiming is that I can just do the switch on the identity matrix. So if I switch these two rows, I'm going to get 1, 1. So I switched the first two rows of the identity matrix. And then you can see what's happening, that when I multiply this thing out, oops, when I multiply this out, the first row, when I multiply this by here, this one is going to hit this row, and I'm going to get exactly the, so this multiplying on the left, this implements the R1 switch with R2 elementary row operation. Okay, on the other hand, if I multiply on the left by, let's say, 1 lambda 1 with zeros, so this is the scaling of the second row by lambda of the identity matrix, right? And if I do the matrix multiplication, then you can see that what's going to happen is that this lambda will hit this row and it's going to scale it. So left multiplication by this implements scaling, right? And similarly, if I take one row of the identity matrix and I shear it by a multiple onto another, then, for example, I might get something like this. This is adding lambda this is lambda times the third row added to the first row, and this implements the shear. Okay, so what this means is that each elementary row operation consists of left multiplication by an elementary matrix, a simple matrix, by a elementary matrix, of one of these three types. Okay, so I start with my matrix A, and then I do one elementary row operation. Let's say this is if this is K by N, suppose this is a K by N matrix. The first row operation gives me this, where this is now a K by K elementary matrix of the type either 1, 2, or 3. Okay, then, and this is still will be K by N, of course. K by K times K by N is going to still be K by N. And then the next step, I'm going to apply the second elementary row operation to that result. Okay, and there's going to be a whole bunch of these. However many we need, until it's in reduced row echelon form. Okay. And if we want to keep track of these operations, we should apply them to the identity as well as A. So in other words, when you draw that bar, what you end up with in the end is the elementary row operations applied to A. That's going to be on the right-hand side. And you're also going to keep track of the elementary row operations applied to the identity. Okay. And so in the end, what you will have is you will have all of the elementary row operations all put together on the left-hand side without A. And then on the right-hand side, you'll have the result of the elementary row operation. And so that's why it makes sense to call this the bookkeeping, because this remembers the operation used. Okay. So we're going to see a application of this on Thursday, several applications of this. But the main point of what I wanted to say in the second part is two things. I wanted to just explain this fact that when you do row operations, doing row operations is compatible with matrix multiplication as long as the row operation is done on the matrix furthest to the left. And that is because of the way that matrix multiplication is defined, that it takes a row from the left and multiplies it by a column on the right. And so if you move that row, it affects the row of the result. And the second thing is that applying elementary row operations is actually matrix multiplication on the left by certain elementary matrices, and that we may want to keep track of those matrices. Okay, I'll leave it there, and we'll pick up for where we left off on Thursday. I'll stick around for 10 minutes of questions.
Okay, so Anatoly has a question.
So I'm wondering how you would represent shearing as matrix multiplication.
Well, okay, so before I show you the answer, let's just go through the concept. So if you want to shear a matrix, that means that you're going to add a multiple of one row to another row.
Right.
Okay. So doing an elementary row operation, okay, is if you do an elementary row operation on a product AB, or let's say XY, then you can just do the elementary row operation to X and then multiply by Y. So what I'm going to do is I'm going to take the matrix in question A, and I'm just going to write it as the identity times A. And then what I can do is do your shear, the shear that you want to do to A. Don't do it to A, do it to the identity map first. If you do it to the identity map and then multiply that by A, you will implement the shear. So in other words, if I want to shear A, this is the same thing as shearing the identity and then multiplying by A. Okay, so in that sense, what you'll see is you'll have the identity, and then if you want to do the shear where you take lambda times the ith row, and let's say this is the row, this is the I1 row, and this is, let's say, the I2 row. If you want to add a multiple lambda of I1 to I2, then you'll just take lambda and add it there.
Right. Okay. Yeah, that makes
so
sense.
that will be the everything else zeros.
Right.
So the lambda will be here because I've sheared this one to a lambda multiple and put it in the row I2. So if you multiply this matrix by A, it will exactly implement the elementary row operation. Okay, right. So elementary row operations can always be expressed as multiplication on the left, and elementary column operations can always be expressed as multiplication on the right. And in both cases, those are square matrices because they're just operations on the domain or the codomain respectively.
Right. Okay, yeah, thank you. That's very clear. Yeah.
Okay.
Okay, so Michael has a question.
Hi, my question is about this change of basis matrices earlier.
Yeah, okay. Let me just go back to there.
So, yes, it was specifically the ones with the standard bases and for the reals as well as the complex.
Okay, yeah.
Yeah, do you think you go down a little bit more? It was where you had all three of them. Yeah, right here. So okay, so the first one, you know, I put in like 1 0. Actually, well, if you look at the third one, actually, so I put in 1 0, and like so I figured that would represent, you know, just the normal unit vector and the real basis, the standard real basis.
Yeah.
And then so then I would get out, you'd get out 1 I, or what would it be? You'd get out one I and one minus I just, it seems like the opposite. It seems like I would be getting out the complex or vice versa. Basically, my question is, I think in a way that makes most sense, is just why is it beta gamma instead of gamma beta?
Okay. So, I mean, I try to like, it's like saying, I built a sequence of technology, right? One after the other, right? And I ended up with this, right? And then at the end, you're like, why is it this and not that? Because it's like the notation was developed so that things would work out. So let me just go over it. So when you see this expression, so you could divide your question into two parts. You could say, well, why is it true? Oh, why is it true that that when I'm interested in the matrix for basis beta prime gamma prime, I just, I have to figure out beta prime to beta, beta to gamma, gamma to gamma prime, right? So the way that things were set up was that this notation of writing the square brackets and something in front and something in the back, the way that it's developed is so that, the columns of this matrix are the expression of the beta prime basis in terms of gamma prime. Those are it's one way, right? There's a convention about what this matrix means. You're supposed to take beta prime and express it in terms of gamma prime and write the coefficients down the columns. Now, if you use that convention, right, then the rule is that when you take, where is it? This is from last time. Yeah, here. Okay, so if you want to know, this is the relationship between matrix multiplication and composition of maps. So if you want to know the matrix of a composition in alpha gamma basis, what you need to do is take the matrix of S with respect to alpha beta, the matrix of T with respect to beta gamma, and multiply them as matrices. Now notice here that when I was asking the question, I didn't say anything about beta, right? This composition doesn't care about beta. But if I want to have a matrix for S, I need to choose a basis beta for the codomain of S and a beta for the domain of T. So what this formula is really saying, the important thing about this formula is the following, that if you have, if you have a sequence of maps from U to V and then from V to W, right? If you want to figure out the matrix representation of TS, what you need to do is choose a basis for V, express S in terms of this pair of bases, express T in terms of this pair of bases, and then multiply the matrices. But it's important that in this theorem, right, the expression of S and the expression of T use the same beta. It's not important which beta, but it's important that they use the same beta. Okay, so anyway, if we go back to the actual problem, okay, this here inside here, this is the expression of a rotation in terms of the beta basis. Beta is the standard basis. This is just the standard basis. Okay, and so because this matrix is given to us in the standard basis, that means that I need to know, I need to put the same basis here for the codomain of the identity, and then my new basis gamma is on this side. So this is telling us that whatever this matrix is, it has to be the coefficients of the gamma basis in terms of the standard basis.
I see. That makes sense. But so then, actually, this is a better example.
It's kind of like there's like two realms, right? Whenever you have two bases, it's like you're in a different realm, like a shadow realm. Like you have to say that if I'm interested in expressing the rotation in this shadow basis, right, then you have to take the shadow basis map it into the real basis, like express it in terms of the real basis, then apply the real map in reality, and then take the result, which is expressed in the real basis, into the shadow basis. So you're transporting, you're going from, one state to another state, doing the operation that and then reverting to the old state. So you have to kind of keep track of where you are when you're doing this.
I see. So what I was thinking earlier is that, so this doesn't mean that if I put in like a standard basis, so in terms of, or in terms of B, so if I put in say 1, 0.
Oh, okay, yeah.
Right,
That's
I would get out. Then
so,
what exactly would get out?
Let me explain. So I think I know what your confusion, where it comes from. So if I take a column vector 1, 0, right, and if I take this matrix now and multiply it by 1, 0, the question is, what does 1, 0 mean in this context, right? This matrix here is being written in the gamma basis. So this 1, 0, if you wanted to interpret this matrix multiplication against this vector, then the interpretation of this 1, 0 would be the first basis vector of gamma, not of beta.
I see.
So, I mean, normally, you see, like when you think about it this way, that when you take a linear map from V to W and you write it in terms of a basis, right, then that means that your linear map dissolves into numbers. It becomes a matrix. And then that matrix can be applied to column vectors of numbers. Okay, but the same linear map can be represented in different ways as a matrix, right? So that means that when you are doing a matrix multiply vector, there's implicitly a basis that's being chosen. And that vector, if it's 1, 0, represents the first basis element. So this 1, 0, this represents a basis vector. Okay, but in this interpretation, it would be the first basis vector of gamma, not the first basis vector of beta.
Right. Okay. That makes sense. Very helpful. Thank you.
The problem is really that, a basis vector, if you have, if you have two bases, E1, E2, and V1, V2, if these are both bases, okay, then you might say, well, what is the vector representation of of this vector of E1? Is it correct to say E1 is 1, 0? Well, it's not. I mean, that is correct, but a better way of writing it would be to say that if you take the matrix of E1 in, let's call these beta and gamma, the matrix of E1 in the beta basis is 1, 0.
Right.
The matrix of V1 in the gamma basis is also 1, 0. Right. So it all depends on in which basis are you writing your vectors.
I see. Thank you.
Okay, so Gurmanjot has a question.
It's just a quick verification. Because given like our identity matrix like our identity mapping matrices, like as do you mind scrolling up just to the picture, like in terms of gamma and beta and like in reverse, so I suppose there would be inverses of each other, right? We could easily check that by considering a bit higher on.
So say what you want to say.
Okay, so no, I just want to verify. So essentially the
you want to
identity
verify.
mapping.
What do you want to verify? Say say the formula.
Okay, so the identity mapping in like of beta in terms of gamma is the inverse of the identity mapping of gamma in terms of beta, right?
You're asking me a question, or you're making a statement. I can't tell. So what happens if you matrix multiply this?
Oh, you get gamma, like identity, like gamma, identity, gamma, and then. and it would be obviously that would just
Can you do
be-
it step by step, please?
Okay, I'm sorry.
So this is using the definition of matrix multiplication
Mhm.
as it is related to composition. So that means that the product of these matrices is equal to the matrix of the composite of the operations, right? Why? Why is this thing true? I would say that the reason it's true is because the basis for the codomain of this matrix here is the same as the basis for the domain of this linear map. Okay, then what's the next step?
Well, the identity composed with the identity is just the identity, right?
Yeah. So now I use what I know about the identity map, correct? And now what is the matrix of the identity written in the same basis in the domain and the codomain?
It's just the matrix identity.
Yeah.
Okay. So
you understand that this is a proof using the results that we have so far.
yes. Mhm.
Okay.
So I'm not sure if this is like.
This means that this n by n square matrix and this n by n square matrix are inverse to each other. So it's just one second.
Okay.
So using these change of basis matrix ideas, you can see that there's a clear relationship with inverting linear maps, which is actually the next thing that we're going to talk about on Thursday. We're going to talk about in detail inversion.
Okay, got it. I guess like this isn't really. I was just like wondering. So in this case, would that mean that like I guess I'm gonna prove this myself, but it's just a question I guess for everyone. Like would any invertible matrix could any invertible matrix be written as the identity mapping in a basis in terms of another basis? Is that?
Yeah. Think about it.
Okay, got it. Thank you.
Okay, gotta go, people. Enjoy the rest of your week. I'll see you on Thursday. And I'll put up the assignment later tonight, the new assignment.